Hi, my name is David Lazar, and today I'm going to present my latest work on metadata privacy. So metadata is all of the data that can be observed by an adversary that isn't protected by encryption. Here we have a chat system with several users, and all the messages between users are end-to-end encrypted and authenticated. The black arrows are messages, and even though you can't read their contents, you can still observe a lot of relevant information. For example, the source and destination of every message, the sizes of messages, and the times at which messages are sent and received. But what can you learn from observing this metadata? Let's look at an example. Take a minute to observe the metadata in this system. What do you learn about the users from their metadata? The metadata reveals who's communicating with whom. For example, we learned that Dan and Aaron are communicating with journalists at the New York Times and at The Guardian. All of this metadata is visible to a passive network adversary, like the Great Firewall of China, which can see the source, destination, and size of every network packet. For some users, like Dan and Aaron, the mere act of talking to a journalist might be dangerous. This makes it tricky for Dan to blow the whistle on his government if his communications are always being monitored. Since we can't eliminate metadata, we instead try to make the metadata not reveal anything useful about the users. For example, we can make everyone's metadata be the same by having users send cover traffic synchronously in rounds. Each round, every user sends a message to the system and receives a message from the system, even if they're not actively in a conversation. And all messages are the same size. By default, users send a message to themselves if they're not communicating with anyone else. Now you, as the passive network adversary, can no longer tell who's communicating with whom. But what if the adversary takes a more active role in trying to figure out who's talking to whom? An active network adversary might do things like drop, delay, or duplicate messages in order to steal metadata. Let's see what this looks like. In this animation, the attacker is doing two active attacks in every round, one on Carol and one on Aaron. Notice that after dropping Carol's message, Fred no longer receives a message from the system. This suggests to the adversary that Carol is talking to Fred. Similarly, the Guardian receives many more messages after the attacker duplicates messages from Aaron, so the adversary concludes that Aaron is likely talking to the Guardian. These active attacks are simple, but very effective. The security goal of this work is to build a system that hides who's communicating with whom from an active network adversary, and an adversary that compromises the chat servers that make up the system. The other major goal of this work is to achieve sufficient performance for voice calls, which means sub-second message latency with a few kilobits per second of throughput for millions of active users. The prior work in this area compromises on security to achieve performance or vice versa. For example, Tor meets our performance goals, but it doesn't provide guarantees against passive or active attacks. On the other end of the spectrum, Pung provides great security guarantees, but its performance is a few orders of magnitude away from supporting voice calls. And other approaches like Karaoke and Herd provide weaker privacy notions. Yodel is the first system that meets all of these goals. More specifically, Yodel is the first system for voice calls with strong protection against passive and active attacks. The system is distributed among many servers so that no single particular server must be honest or trusted to provide privacy, and the system achieves horizontal scalability to support many users. The system achieves sub-second latency for 5 million users with 100 servers running over the internet. The system builds on two key insights: self-healing circuits and guarded circuit exchange. But in this talk, I'm just going to focus on self-healing circuits. Yodel's approach to handling active attacks is to rely on an honest server. Here, we're animating the same active attack from the previous slide, but now, an honest server can remove duplicate messages and fill in message drops to make the active attacks ineffective. Notice that everyone that submits a message to the system receives exactly one message back. Carol's message was dropped, so the server fills in an indistinguishable dummy message for Fred. Similarly, the server removes duplicates from Aaron, so the Guardian only receives one message in each round. Now an active attacker can no longer tell who's talking to whom. But we've made a big assumption that the server is honest. How can we defeat these attacks if the servers are malicious? Yodel uses a mixnet to distribute the task of hiding metadata among multiple servers. Now we have 3 servers instead of just 1. Messages flow from left to right through these servers, and the white dots represent input and output positions for messages. Users onion encrypt their messages to force their messages to go through all these servers in a particular order. For example, here we have Alice and Bob, who are going to send a message each through the mixnet. At each hop, the servers remove a layer of encryption, shuffle the messages, and send the results to the next server. The last server receives the messages X and Y. The mixnet ensures that as long as one of these servers is honest, say server 2, and hides its permutation from the adversary, then the adversary doesn't know who sent which message. Unfortunately, mixnets have a high CPU cost. The most expensive step in this process is decrypting the incoming onions from the users. Each server has to do a public key operation for each incoming message before it shuffles the messages. And I indicate the public key operations with the modular exponentiations inside of server 2. For 1 million users, even a powerful server with many cores will spend several seconds decrypting onions, which already puts us over our latency target. Yodel solves this problem with a mixnet design based on hybrid encryption. In Yodel, users establish paths through the mixnet called circuits using public key cryptography. To create a circuit, a user sends an onion through the mixnet that contains a symmetric key to use at each hop in the circuit for following messages. When each server unwraps this circuit setup onion, it saves the symmetric key for its position in the shuffle. So let's see how this works by tracing Alice's circuit setup onion as it goes through the mixnet. So the first server receives the onion, it installs the symmetric key, shuffles the messages, sends the onion to the second server, which repeats the process, and so on. And finally, the last server also receives a special circuit endpoint ID, which identifies the end of the circuit, which is how users connect to the circuit to receive messages. Once these circuits are created, users can send many messages through their circuit with far less overhead. Users send messages through the circuit synchronously in what we call subrounds. In a subround, every user onion encrypts a message, like a voice frame, using the symmetric keys that they installed for their circuit. At each hop, the server removes a layer of onion encryption, reapplies the shuffle that it generated during the circuit establishment phase, and sends the results to the next hop. Every subround uses very little CPU, so we can pipeline many subrounds to improve throughput. In our experiments, we run roughly 4 subrounds every second, but the exact timing depends on our voice codec. The challenge with reusing the same permutation for many messages is that now an attacker has several chances to learn the permutation of the honest server, say server 2. Suppose the adversary drops this message between server 1 and server 2. It might observe a gap between server 2 and server 3, and now it learns where that first message ended up in the permutation. And it can keep repeating this attack for every message to eventually discover the entire permutation of server 2. Yodel's solution to this problem is self-healing circuits. Whenever circuit messages to an honest server are missing, the honest server fills in the gap with a random noise message. The arrow inside of server 2 indicates the noise message that was generated for the missing input message. Now, the output from server 2 has no gaps, so the attacker doesn't learn anything by dropping a message. The circuit messaging onions are symmetric key encryptions that are indistinguishable from random. The onions are also unauthenticated, which enables a server to generate random noise that's indistinguishable from a real user onion during the self-healing process. This ensures that all outputs from an honest server are always indistinguishable, so an honest server never leaks any metadata during the circuit messaging phase. In other words, all active attacks, including message drops, duplications, and tampering attacks, are healed by an honest server on the path. So far, I've described how users send messages through the mixnet while hiding who's sending which message. To receive messages, users connect to one of these circuit endpoints on the last server in the chain. Here, Alice and Bob connect to each other's circuits in order to hear each other over the system. But there's an interesting challenge here. How do users know which circuit endpoint to connect to? We rely on an external metadata private messaging system for users to exchange information about their circuits. They need to exchange a single message with their circuit endpoint ID, but the adversary might cause this exchange to fail. The solution to this problem is called guarded circuit exchange, and I'll leave it to you to read our paper to understand our solution. Finally, to support many users, Yodel uses a scalable mixnet topology, which we borrow from our karaoke paper from OSCI 2018. In the scalable topology, users are sharded among many servers. However, to meet our security goal, messages have to traverse many more servers to ensure that their messages get mixed together. In our paper, we prove that if 20% of the servers are malicious, then users will mix with overwhelming probability if the messages pass through 15 hops. However, if the latency between these hops is high, say 45 milliseconds, that means that roughly 700 milliseconds will be dedicated just to 700 milliseconds of end-to-end latency is just due to the network latency alone. And we're going to see how this plays out in our evaluation. One of the most challenging aspects of this project was actually implementing Yodel. For example, initially we used TCP for all network connections because we were in the mindset that dropping packets was unsafe. But with TCP, we found that a packet drop anywhere in the network stalled the whole round. Then we realized that switching to UDP was safe because self-healing ensures that packet loss leaks no metadata. We discuss other interesting implementation challenges in our paper. We ran our experiments over the internet using Amazon EC2 instances located in several countries. Each of the servers in each of these 5 countries had 36 cores and 10 gigabit links between the nodes in the same data centers. And we also simulated millions of users in each of these regions. The maximum one-way latency between regions was 45 milliseconds between Virginia and Frankfurt. And this latency is what dominates our end-to-end latency for users' voice packets. In this experiment, we measured the one-way latency of voice packets as we varied the number of users from 0 to 8 million. The results show that with 5 million active users, Yodel is able to achieve our performance goal of sub-second latency. We can also see that with 0 users, we're around our 700 milliseconds of latency just due to that 45 milliseconds between hops. All right, now I'm going to play a short demo of what Yodel sounds like. So my friend Joanna and I had a short conversation over Yodel with 5 million other users actively using the system, and we simulated these users as we described in our setup. The audio is recorded from Joanna's laptop, so you'll hear her voice directly, and my voice is recorded through Yodel. So just to give you some context, we're using a low bitrate voice codec here, so which allows us to achieve our performance, allows us to achieve good performance, but you can judge for yourself what you think it sounds like.
Hi, Joanna. It's David. Can you hear me?
It's a little fuzzy, but I can understand you just fine. Will I be able to use Yodel from my phone?
That's the next step. The problem is that Yodel Discover traffic drains the battery on a phone pretty quickly. But I think this will be an interesting research challenge going forward.
That sounds tricky. Maybe you can reduce the latency too.
That's the plan.
So in conclusion, Yodel is the first system for voice calls with strong metadata protection against passive and active attacks. The system doesn't particularly trust any single one of these servers, but instead, the trust is distributed among many servers, and we achieve horizontal scalability to support many users. And our experiments show that Yodel is able to achieve sub-second latency for 5 million users with 100 servers running over the internet. Thanks.
Henry Ching from Square. So just wondering, how did you do the simulation of the 5 million users? What level were you simulating at?
So what we did is we actually generated a bunch of extra messages at the start of the round. The servers would generate these messages. So we didn't actually run, so we had two real clients that were running the voice system, me and Joanna. And then we had the servers generate the user messages ahead of time.
Did you measure the latencies experienced by each of those 5 million messages?
No, I just measured the latency of our system. And normally clients would generate these messages. So we didn't want to spin up all the servers to generate, run 5 million clients. So we just had the servers do it all ahead of time.
Thank you.
Hi, I'm Shagufta from UIUC. Very nice talk, and I like the idea. So I have one confusion. So when there is no communication going on, you are sending some dummy metadata. It's a very nice way to disguise yourself or the users. But I was wondering that how much impact will it have when there are heterogeneity in the network, A, and B, when there are other traffics in the system. And my second question is, maybe it's a very basic question. So does it require any central authority to certify these servers, or who will bootstrap the system as it's an end-to-end secured system?
Can you repeat the first question?
Okay, so the first question is when there is no communication going on, you are sending dummy metadata.
Yeah. So each user is engaged in a voice call all the time.
Yeah, so I'm wondering that what will be its impact when A, there are heterogeneity in the network, and B, when there are other traffics in the network.
Okay, so let's say messages get dropped during a voice call. So what happens is that users would recognize that packets are dropped, so they'll hear noise in their audio, for example. But there's not much we can do with that. So everything is UDP. We don't retransmit. We just move on to future voice packets.
Okay. So
but we set in all of our experiments, we experienced less than 0.1% of loss across the internet.
Okay. And at that time, did you experiment in this experiment? Was there any other traffics in the system, or you just experimented only with your own traffic?
This is just all our traffic. We
All
controlled
your
all of our
traffic,
instances,
okay.
but it was running across the internet, across Amazon data centers.
Okay. Sounds. And the second question was that who will, does it need any central authority to bootstrap the system or to certify the servers, or?
So we talk about how we envision this thing getting deployed in our paper. Ideally, we should have a bunch of different people running these servers in different countries. Actually, one of the biggest challenges is the maximum latency between any two hops dominates the end-to-end latency for users. So we kind of played a clever trick in our paper, and we tried to locate these servers mostly in Europe and then some in the US. But I think it's an interesting challenge how you actually deploy this while still maintaining the latency.
Thank you.
Hi, Yodel from EPFL. Do all users go through the same chain, same order of servers?
No, so I kind of focused on this single chain topology for most of the talk, but we actually use the scalable topology, and users pick random paths through the network.
And can they pick non-random paths so that their latency would reduce?
So other systems have slightly different assumptions. Like if you're willing to trust your first hop, for example, you can reduce the length of your path and improve latency. But our design is that we don't want to trust any particular server on your path, but instead we choose paths that are long enough so that you hit enough honest servers on your path to guarantee security.
Okay, thank you.
Yeah.
And let's thank the speaker one more time.